All right, welcome everybody. Welcome to lecture 12 of CS 188. A couple of announcements. Your homework 5, reinforcement learning, has been released. This is due on Monday. Your project 3 on market decision processes and reinforcement learning has also been released. This is due next week, Friday, 5 p.m. And today we'll announce the project 2 mini contest results right after break. Any questions about logistics? All right, let's get started with technical materials then. We have a little bit left in reinforcement learning, which we'll do first. We'll look at policy search. So the problem with what you covered so far is that the policies or the Q values that will perform best are not always the ones you find through Q learning. And the reason that's the case because when you run Q learning, what you're trying to optimize is this self-consistent set of equations, the Bellman equation. You want this to be as satisfied as possible. And you try to get your Q values to satisfy that. But you're not zoning in on whether action 1 or action 2 might be better between the two of them. You're just zoning in on that self-consistent set of equations. And so what policy search will do for you is zone in on exactly which action is the better one. So Q learning's priority indicated here. Get Q values close. That's a modeling thing. Get good Q values. But what you really care about is which action you should be selecting. That means you want to get the ordering of the Q values right. And so that's a different objective. This one that will come back later in this class too when we look at classification. Some models just try to be descriptive. Other ones are directly optimizing for predictive value. All right, so the solution would be to learn policies that directly maximize rewards rather than somehow try to predict values. What policy search does, which is probably the simplest way to get there, but a very popular approach, is you start with an OK solution. So you have a policy represented by your Q function. Your Q function is, let's say, a weighted combination of features. That's your starting point. And then you start rolling out according to your Q function. You play. You see how well it works. Then you might nudge one of the weights. You roll out again. You see if it works better or worse. If it worked better, you keep the modified weights and you repeat. If it turned out to be worse, you discard the modification of the weights, go back to the older ones, and give it another nudge, see what happens. Very simple approach, but this can improve your policies quite a bit. So concretely, you might start with your linear combination of features as your starting point, and then you do this nudging procedure. Things we have to answer. How do we know when we change the weights whether the policy got better or not? If it's a deterministic system, that's easy. You can just roll out and compare. If it's a system with stochasticity, it's much harder. Because sometimes you might do better, sometimes you might do worse. And so then you might need many samples until you get a reliable estimate of how good your current policy is. The catch with this approach is that if you have a lot of features, so a lot of weights that you try to optimize in your policy, this can quickly become impractical. But if you already have pretty good weights and you just want to improve them a little bit, or you have a small set of weights, this might work out very well. Better methods for policy search will exploit look-ahead structure, which means essentially combining value function estimates with policy search. Be clever about how to sample and change multiple parameters in one iteration. These are things we're not going to cover, but if you want to learn more, you can look up things like policy gradient methods and actor-critic methods, which will do these kind of things. But let's take a look at how well even just this approach can work. So what are we looking at here? This is a helicopter, and the task is for the reinforcement learning algorithm to learn to control the helicopter. What do you have to do? What does it mean to control one of these helicopters? There are 4 control channels. Channel 1 is the average angle of the main rotor blades. So your main rotor blades sweep through the air, typically about 1,800 revolutions per minute for a helicopter like this, and there will be angle of attack. The more positive you make that, the more air you're pushing down, and so the more thrust you generate. That's the first control channel. Second control channel is the tail rotor. The reason you want to control the tail rotor is because you might want to decide where you are facing. So different angle of attack for the tail rotor will give you a different amount of thrust on the tail rotor, will make you face a different direction. What you're actually controlling is the angular rate around your vertical axis. Third axis of control is to make your helicopter roll, and then the fourth one is to make it pitch. The way you do that is you actually change the angle of attack of your main rotor as it sweeps through the air. For example, you have bigger angle of attack there, smaller angle of attack there, so differential thrust left and right. That allows you to roll, or if you do it front back, allows you to pitch. So overall you have 4 control channels. One is vertical thrust, and the 3 others correspond to angular rate around each of your 3 main axes. Kind of simplest thing, if you have not flown a helicopter that might be comparable to this is, let's say you are controlling a big broom on the palm of your hand, and you try to balance it and try to get places. Same thing there. If you want to move forward, you can't just move forward because it'll just tip backwards. Same with helicopter. You actually can't move forward. You actually have to point your nose down, and only then can you move forward. Same thing for that broom. You have to point your palm down, and then you can push forward to move forward. You constantly have to adjust. This broom might fall off the palm of your hand very easily. If you close your eyes, you don't pay attention, it'll fall over pretty much instantaneously. Same for helicopters. If you don't pay attention, they'll drop out of the sky like a rock. That's one of the disadvantages of helicopters compared to planes, where even when the plane is essentially, the engines are all dead, you just keep floating. For a helicopter, a little trickier to stay alive. Now, this is a hard problem. What happened in 2002 is Andrew Ng was wrapping up his PhD thesis work here at Berkeley in Mike Jordan's group, and Mike challenged him and said, you know, you've done a lot of great work on reinforcement learning. Helicopter flight is a really hard control problem. Let's see if you can crack helicopter flight with reinforcement learning. Andrew got some results at Berkeley, got a job as a professor at Stanford, then extended the results there, and what we're going to look at here is the results that were gotten there in 2004. So what's going on here? This helicopter is perfectly stabilized. As you now know, that's actually really, really tricky because it just wants to drop out of the sky. It's constantly kept in the air against its own desire, so to say. Not only is that what's happening, the helicopter is inverted. How does that work? Any thoughts? Over there.
It's stuck in this local maximum because moving it backward with the right configuration will initially pass through a less stable.
So that's a really interesting thought. Let's say you start inverted and you try to flip over. That will be a very difficult maneuver. And now your reinforcement learning algorithm, well, the policy isn't that great yet, and when you try to flip over, you'll probably crash. Absolutely true. That's likely to happen with these reinforcement learning algorithms because you need to learn for a while before you get somewhere. So it's a little different than what's going on here, though, because what's happened here is that the learning was first done in simulation, where there was a lot of time to learn a lot of things, and actually was intentionally flying inverted. So it wasn't a coincidence. It wasn't just like, oh my God, it converged on something inverted. It was, let's see if we can fly it inverted and see if it can succeed. How do you fly inverted with a helicopter? Told you about the angle of attack of the main rotor, right? Make that negative. If you're flying normally, you're going down very quickly. Make that negative. When you're inverted, you actually stay in the air. It's actually not that different from flying straight up. It's just that the body is now above the main rotor disc rather than below. It's actually more efficient to fly this way. Any thoughts why? Over there.
Because of the weight of the, I don't actually know if this makes sense now that I'm saying it. the weight of the helicopter is like supported by the rotor instead of like the weight of the helicopter pulling down on the rotor.
So it's something about where the weight of the helicopter is and what it's doing. That's in the right direction. We're going to need a little more detail to really show that this is more efficient. But it's the right starting point. Over there.
The air coming out has direct thrust downward instead of having to deal with going around the helicopter.
That's the complete answer. So what happens if you do an analysis of aerodynamics and you analyze how a rotor disc works, you'll see that there will be an intake velocity that's induced by the spinning. Let's call that V. And then the outgoing velocity will be 2 times V, approximately. But that's a crude calculation. If you're flying normally, the 2 times V air goes over the body of the helicopter, dragging it down. Whereas you fly inverted, only the 1 times V air goes over the body of the helicopter, not pulling it down nearly as much because air drag is quadratic in the air speed, so you get 4 times more drag on the helicopter body if you fly normally compared to flying inverted. For our project with the Stanford helicopter at the time, I was a PhD student in Andrew's group, we found that for acrobatic helicopters we could generate 3 Gs, so 3 times the gravitational force, 3 Gs of acceleration inverted, but only 2.7 Gs of acceleration flying straight up. So it's a 10% difference in kind of the max capability you get inverted versus regular flight. All right, so that was policy search in action, optimizing directly for performance of the helicopter. This was done, you didn't see the learning here. The learning was many, many rounds of iterations of simulation in a simulator where the helicopter initially would actually not fly reliably, but over time, the weights in what corresponds to the Q function will get better and better and better until it could reliably hover, inverted in this case. Any remaining questions about reinforcement learning? Because we're going to switch gears here. Yes?
I have a question about the grading of this. Would that be done like a computer simulation or?
So that's a good question. Whenever you want to do reinforcement learning with a robot, it's often difficult to directly run it on the robot. It's possible, but it's often dangerous. And if the robot is expensive or it's a helicopter, it's kind of expensive and you don't want to crash it, you need to be very careful about what you do. You can do various things. One thing you could do is you could set up a safety pilot, which you probably want to do no matter what, who can take back control whenever things seem to be going wrong. And that was done here. But in addition to that, initially things will go so wrong when it doesn't know much yet. It's actually better to first build a model for your helicopter, run reinforcement learning in simulation, then whatever you find there, from there go to the real helicopter and see what happens. So there's a two-phase approach there, first in simulation, then on the real helicopter. Any other questions about this or reinforcement learning? All right, let's switch gears. So our status in 188 is that we're done with part 1, which is search and planning. We've seen how AI methods can solve problems in search, constraint satisfaction problems, games, market decision problems, and reinforcement learning. What's up next is part 2, probabilistic reasoning, and then after that we'll get to part 3, which is machine learning. What will probabilistic reasoning give us? Some examples. Diagnosis. Let's say you want to diagnose the disease a patient has. You might get their temperature, you might get their pressure, blood pressure, you might get maybe some explanations of how they're feeling, but that's not a direct measurement of their disease. It's an indirect measurement, it's a noisy observation of what might be going on. Can you infer from that what the most likely disease is that they're having? Speech recognition. With speech, you get sound waves that reach you or reach a microphone that then passes it on to a computer. How to transcribe that into written text. It's a very difficult problem because there's no one-to-one mapping between text and speech. Tracking objects. Let's say you are building a drone and you want that drone to track you as you snowboard down some slopes in Tahoe. Well, that drone needs to track where you are. But it might have to do that just based on camera readings, which don't explicitly tell you where you are. It's just a bunch of pixels from which you have to infer where the person might be. Robot mapping. Let's say you're a rescue robot and you're going to a site where something bad happened. Let's say an earthquake, it's all rubble, or maybe it's a fire and you want to go in and find people and rescue them. You might not have a map when you start out. Or you might have had a map, but because of the earthquake, things have changed drastically, and you can't rely on that map anymore. Now, when you go in, you'll get measurements. All of these measurements will be noisy. For example, a camera reading doesn't tell you where things are. It just tells you in that direction there's white, in that direction there's blue, and so forth. Can you, from that, infer what the structure is of the building that you're in? Genetics, from seeing phenotypes, can you infer what the underlying genotype might be and then maybe make predictions about whether it's good, let's say, for two people to mate, or there's maybe a risk factor and you might want to warn them? Error correcting codes. Typically, when you communicate over a channel and you send some bits, some of these bits will be flipped by the time they arrive at the other side. A very simple thing to address this would be to say, instead of sending each bit once, I'm going to send each bit 3 times. And so now I send 3 ones instead of 1 1, and with the 3 ones, you're like, well, if one of them gets flipped, there's still 2 ones, so I know that's the majority, so it's probably a 1 that was intended, and I'm going to understand that this was a 1 being sent. That's very inefficient. If you need to send 3 bits for every 1 bit that you send over. Error correcting codes essentially look at how can you take a sequence of bits, re-encode it in a slightly longer sequence of bits, but in a way that if a few bits get flipped, you can still probabilistically infer what the most likely original sequence of bits was that the person was trying to encode and correct for that. So there are many applications of probabilistic reasoning. So probability is our starting point. Here are the concepts we're going to cover today. Random variables, joint and marginal distributions, conditional distributions, the product rule, the chain rule, and Bayes rule. Those will be our main tools that we'll be working with. Inference, independence, and all of these will be things you'll need to know really, really well to follow along in all of the next lectures. So today is a review, hopefully. If it's not a review, make sure that after more studying of this material, it feels like today was a review, because we're going to be using a lot of this, and we're going to assume that you know this really, really well when we're working with Bayes nets in the next 4 or 5 lectures. All right, let's start with a motivating example. So we have a grid, and the ghost is actually invisible in this scenario. So we don't know where the ghost is. But we know it's in one of the grid squares. There's a sensor available to us that we can use. We place that sensor in a grid square. It'll light up green, yellow, orange, or red. The color corresponds in a noisy way to distance to the ghost. So typically, if you're on the ghost with your sensor, it'll sense red. It's not guaranteed. If you're 1 or 2 away, it'll sense orange. If you're 3 or 4 away, it'll sense yellow. 5 or more away, it'll sense green, but all of these are noisy measurements. For example, when you are 3 away, the sensor will sometimes be red, sometimes be orange, usually be yellow, and sometimes read off green. So you don't get a very direct measurement, just a noisy version. This is true for many sensors. For example, if you have a laser rangefinder that's trying to measure distance to a wall, it's not going to tell you exactly how far away that wall is. There's going to be some variance around it. And this is true for almost every sensor out there. So let's take a look at what we can do in terms of finding the ghost. All right, so here's our environment. Let's see if we can track down the ghost. One ghost in here. Let's see. How about we measure over here? We might be reasonably close. Let's measure maybe here. It's probably in the other direction. This is pretty good. High chance of the ghost being there, but who knows? It's not guaranteed to be red only when you're on the ghost. So let's do a few more measurements. All right. All right, what do you think? Where's the ghost? This green here makes me a little uncomfortable going here. We have a bust action, which we can use once. We have one bullet, so to say, to blast the ghost. Where are we going to go for it? People are saying the red one. Okay, let's see what happens. We got it. got the ghost. So this worked out. Were we guaranteed to get the ghost? No. But we had a high chance based on the measurements that the ghost was there. We took our chances and it worked out. What we'll look at today is the underlying calculations that you can do to know exactly what the probability is that the ghost was in that location. Or any other location for that matter. All right. So the general situation is one where we have some variables that are observed. This would be the sensor readings. And the agent knows certain things about the state of the world thanks to that. Then there are unobserved variables, usually the variables we're interested in. Where the ghost is an unobserved variable until we use the hit action, at which point we find out, but it might be too late if we use it in the wrong place. Then there's a model, and the model relates the variables to each other. It says, if the unobserved variable takes on this value, then it's likely that the observed variables will take on these and these values. Probabilistic reasoning gives us the mathematical framework to make those inferences, where you go from information that you can read off to statements, probabilistic statements about the unobserved variables. Okay, so what's a random variable? Random variable is some aspect of the world about which we may have uncertainty. Okay? For example, random variable capital R. Is it raining? Could take on the value true or false. Temperature. Is it hot or cold? Two possible values. How long will it take to drive to work? Where is the ghost? So these are examples of random variables. We will denote our random variables with capital letters. So whenever you see a capital, you know it's a random variable. Like variables in a CSP, they have domains. For example, R could be true or false. As a shorthand notation, we'll often write this as plus R or negative R. How is that a shorthand? Plus R corresponds to R equals true, and similarly for negative R. So it's a much shorter way to write the exact same thing. Here, temperature could be hot or cold. The domain could be continuous. We're not going to do continuous probability in this class, but the ideas that we're presenting in 188 carry over to continuous probability distributions too. And this could be multivariate random variables. You could take on a pair of coordinates as the value of your random variable. Okay, for each random variable, we'll think about what the distribution is. For example, temperature. We might have a distribution that is 50-50, hot versus cold. Weather, we might have a distribution over 4 possible outcomes, some probability of sun, rain, fog, or meteor shower. These tables here, these numbers have to sum to 1, and they all have to be positive. That's what's required to make this a probability distribution. All right. So our unobserved random variables have distributions. The distribution corresponds to a table of probabilities of values, and each value has to be positive, and they all sum to 1. Shorthand notations that we'll use. If all domain entries are unique, meaning that, for example, temperature could take on the values hot or cold, weather cannot not take on those two values. So if the values are unique, you can shortcut this to this. So we say P, hot. Really, we are saying probability that the random variable temperature equals hot, just a shorthand notation. All right, what we'll be interested in is joint distributions over many random variables. For example, n random variables, x1 through xn. Such a distribution will assign a probability to each joint outcome of all the variables, which shorthand we'll write this way over here. For example, here's a joint distribution over temperature and weather. The probability of hot and sun is 0.4. Same properties need to be satisfied. Each entry needs to be positive, and they all need to sum together to 1. So this here sums to 1. What is the size of the joint distribution if we have n variables? Each can take on d different values. Any thoughts? Over there.
D to the n.
So the suggestion is d to the n. Why d to the n? Well, for the first variable, you can choose out of d values. The next variable, you can choose out of d values, and so forth, until you've chosen a value for all variables, and you've had d to the n choices to make. Okay, or d to the n options to choose from. For example, here we have domains of 2 for each, and so this here is size 2 to the 2. If you have a large number of variables, this quickly becomes impractical. We'll worry about that in the next 4 or 5 lectures. For now, let's assume we can handle this. Probabilistic models correspond to joint distributions over a set of random variables. So probabilistic model consists of random variables. Assignments to these variables are called outcomes. So the combination hot and sun is an outcome. The joint distribution says how likely each of these outcomes is, has to sum to 1, and only certain variables might directly interact in some cases, and that's something we'll exploit in the future. For now, the only way we know how to specify joint distributions or probabilistic models over many variables is by providing a full table. That's what we'll do for today. Look at the similarity to constraint satisfaction problems. Distribution over 2 variables, constraints over 2 variables. In CSPs, we say whether certain combinations are allowed or not, but we don't associate a weight with that. In joint distributions or probabilistic models, we associate weights with each combination of the instantiations of the variables. Okay, what we'll care about a lot is events. So we're not just going to work with the joint distribution and look at individual entries. We care about things we can infer from that full joint distribution. The probability of an event is the sum over all outcomes that belong to that event, the probability of that outcome. So if you have a joint distribution for any event, which is a set of possible outcomes, you can compute the probability by looking in the table, grabbing the corresponding entries, and summing them together. So let's do some examples. What's the probability of the event hot and sunny? Any thoughts? Easy one, right? Hot and sunny. Only this row is compatible with that, so 0.4. What's the probability of the event that it's hot? Well, which outcomes have hot in them? It's happening here, so this is 0.5. How about hot or sunny? Well, hot's happening here, sun is happening here, so it's these 3 rows satisfy the definition of this event over here, and this gives us 0.7. Typically what we'll care about is that we'll start with a really large distribution, meaning many, many variables, and the event that we care about will be over a small subset of the variables. Might have a distribution over 100 variables, the event only involves 5 variables. All right, let's look at a few more here. What's the probability of plus x and plus y? Here's 0.2, indeed, because this is the corresponding row. What's the probability of plus x? What do we think? And here's 0.5. Why? Because plus x is sitting over here. What's the probability of negative y or plus x? Negative y, plus x, so 0.6. All right, now let's move to marginal distributions. Marginal distributions are subtables, where we eliminate some of the variables from the joint distribution to get a smaller table. Okay? The way we eliminate them is by collapsing the rows where that variable is changing and adding things up. Let's look at an example. So let's say we start with a joint distribution over 2 variables, temperature and weather. And we're interested in the marginal distribution over just temperature. All right, so we're interested in building a table for just temperature. The way we get this, the way we get the 0.5 is by looking at what's the probability of the event hot, these 2 entries here, sum them together, add it over there, same thing over here. And this here is the equation that encodes that. Okay, let's look at another example that you can do yourself. Here is, again, a joint distribution. Let's build the marginals. So let's look at the marginal distribution for x. What is the entry we fill in over here? Any thoughts? And here is 0.5. Then how about the next one? Also 0.5, two ways to find that. One way to find the next 0.5 is that it has to sum to 1. So you know the only way you can sum to 1 is by also having 0.5. If you're not so sure about your calculations, you might want to then calculate the one for negative x by summing these two together. You find 0.5, and then you can sanity check that indeed everything you did sums to 1. We can also compute the marginal for the other variable, for y. What's the probability for plus y? And here's 0.6. Let's see, plus y adds up to 0.6. Negative y, the complement of that, 0.4. The key concept that will come back and back when we work with joint distributions is that of conditional distributions. The reason we care about conditional distributions is because we care about how variables interact. We care about if we have a sensory reading, let's say if we measure yellow, conditioned on that observation, what is now the distribution over the location of the ghost? Okay? So conditional probability for an outcome A given we have B is this is definition here, is the joint probability of A and B occurring together divided by the probability of B occurring. So you're measuring the fraction of the time that A and B occur together when B is occurring. So in probability space, you'd be knowing that B is occurring, so you're living in this circle over here. And then what is the probability that A will happen now? It corresponds to this slice over here. And so this fraction of the time when B happens, we have that A is also happening. All right, let's do a calculation for this. So let's look at the conditional probability for W equal S, given temperature equals cold. We can just follow the definition. So when you're asked to compute this, you can write this out. Probability of W equals S, comma, temperature equals cold, divided by the probability of temperature equals cold. Then we need to look in the table to find what these things are. This one actually occurs over here. S and C is right here. Temperature equals cold. That actually does not directly appear, but it's an event that is a combination of these two over here. So we have, this is equal to probability of, let's abbreviate it, S and C divided by the probability of S comma C plus the probability of rain comma C, which is 0.2 over 0.2 plus 0.3, which is equal to 0.4. All right? Okay, let's take 30 seconds, or let's take a minute for you to calculate these three over here, and then let's report back out a minute from now. All right, let's see what you got. Any suggestions for the first one here? Who was the number for this one? Over there?
1/3.
1/3. How do we get the 1/3?
By taking the probability of having divided by the total probability of y plus y.
Okay, and the top one is 0.2. The bottom one is plus y here, so 0.6, which gives us 1/3. Great. How about the next one? Negative x given plus y. 2/3, right? The complement of the 1/3. How about negative y given plus x? Over there?
3/5.
Say it again?
3/5.
3/5. Okay, let's take a look. This is going to be probability of negative y and plus x divided by probability of plus x. Negative y and plus x is sitting over here, which is 0.3. Plus x is happening here, which combines to 0.5, and we have 3/5. Great. Now that we know how to compute individual conditional probabilities, we can start computing conditional distributions. What that means is we compute condition on some variables taking on particular values. What is the distribution over the other variables? Okay? So here's our joint distribution. We're interested in the conditional distribution for weather given temperature equals hot. We can use the procedure we just covered to find these two entries. So that's a conditional distribution right there for temperature equals hot. We can do the same thing for temperature equals cold. And here we have another conditional distribution. Okay? So that's what a conditional distribution looks like. It's interesting to note that for a conditional distribution, only the variable appearing up front here appears in the table. The one in the back, because it's fixed, does not need to be a column header because it's not going to vary. And so you just have it at the top here, no variation over it. All right, combined, we will write this as the distribution for W given T. So both capitals here. Here, T is left as a variable indicating that we're interested in the conditional for temperature equals cold and the conditional for temperature equal hot. And we combine both of those with this notation over here. All right, now when you compute these conditional distributions, which will be the main thing we'll be doing in the next 4 or 5 lectures, what do you need to do? Let's say we're interested in this conditional distribution over here. We've seen how to compute individual entries. So we know one of the entries is going to be this one, where weather equals sunny. We know how to compute that one. This is the math we do to compute it, and here's the numbers. That gives us one entry in the table. The other entry would be weather equals rain. We can do the same kind of math, fill this all out, gives us the other entry in the table. Combining this, we get our conditional distribution. What's interesting to note here is that there's a lot of shared computation. If you look at this calculation here is the same as this calculation here, because these are the same. Why are they the same? Because this is the same. In each case, you are dividing by the probability of the thing that's sitting in the back here. You're dividing by the probability of temperature equals cold. You can exploit that, especially when your distributions are large. You have a lot of entries to compute. You might not want to recompute that denominator every time again. In fact, there's a very simple thing you can do. If you realize that there is shared computation here, that the bottom is always the same, you can say when I'm computing a conditional distribution, what's happening is if you look at the calculation, at the top, 0.2, 0.3, those are the entries consistent with the evidence. temperature equals cold is the evidence. We're conditioned on temperature equal cold. We just select out those rows and we dropped these. After we've done that, we essentially found what's at the top here. Then all we need to do is now compute the denominator, which we know actually corresponds to the sum of these two entries. That is the probability of cold. That's what we have to divide by. And so we can just select the rows that are consistent with the evidence, then look at the numbers here, compute their sum, divide by that sum, and we get our conditional distribution. So mechanically, this is very, very simple to do when you go from a joint distribution to a conditional distribution. This is called normalization. The normalization step refers to the fact that you do this thing over here. You go from a table given this way, then you divide out the probability of cold to get a normalized table. Generally, what this looks like is you compute a conditional for x1 given x2. You'll always have at the bottom a summation over consistent entries in the table. And so the normalization procedure is always looking at all the consistent entries in the table, sum them together, and divide by that. So let's try to do this. Step through this for this particular table over here. We're interested in the conditional of x given the evidence that y equals negative y. First step, we just select the joint probabilities that match the evidence. So which joint probabilities match the evidence? Negative y is sitting here and here. So we end up with x, y, p. We have negative y, we have plus x, negative x, 0.3, 0.1. That's our selection. Now the normalization trick tells us all we need to do is now sum these entries together, which gives us 0.4, and then divide every entry by that to get the conditional distribution. So to get the conditional for x given negative y, we end up with x and the probability here, and we just have plus x, negative x, 0.3 over 0.4, 0.1 over 0.4. Okay, so if you look in the dictionary and you look up what it means to normalize something, it means to restore it to a normal condition. So that's the everyday meaning of the word. What does a normal condition mean for probability distributions? Well, for probability distribution, a normal condition means that everything sums to 1. So the procedure comes down to compute some constant z, that's often how we'll denote it, which is the sum over all entries in the table, and then divide every entry by z. If you're asked to normalize this table over here, sum is 0.5, you divide everything by 0.5, and there's your normalized table. How about this one? Still the same idea. To normalize this table, you sum everything together, which in this case sums to, let's see, 50. You use that 50, you divide every entry by it, and here is your normalized distribution, starting from an unnormalized distribution, getting it normalized. Any questions about normalization? All right, let's take a break here then. After the break, we'll look at contest results and wrap up our probability treatment for today. All right, let's restart. For the beginning of the second half, let's look at the Project 2 mini contest. So the Project 2 mini contest, what you got to do is you got to design an agent that drives if you're on your own side, you're ghosts. You get to defend your territory here. Once you cross over, you become Pac-Man. You can start eating food pellets on the other side. The goal of the game, you win if you eat more food pellets than the other player, or if you clear them all out. You also need to bring them back. It's not enough to just get onto a food pellet. You also need to bring them back to your own side to actually get the point. Okay, so let's look at some fun names of teams participating in the competition. I don't think this team won. Eigenvalues is one thing. There's something related that allows you to do better, apparently. Let's look at the top 10. So, in our top 10, at number 9, Ghost Killer, Gauthier Dipedal. Number 10, Meh by Jeffrey Lynn and Benjamin Murphy. Well, this is kind of weirdly going out of order. Not sure why the GSI in charge set it up this way, but I guess we'll run with it. At number 6, we have Michael Jang. At number 7, we have Why Bother, Alan Guo and Patrick Yang. At number 8, we have Pack Lives Matter by Ryan Goy and John Noonan. At number 4, we have Eigenvectors. At number 5, we have Happy Agent by Stephen Chu and Liam Leahy. Let's congratulate all of them. Then let's start looking at our top 3. Our top 3 in alphabetical order are QQ, also known as Broken Bot, by Zhongxia Yan and Brandon Lin. Do you happen to be here, Zhongxia and Brandon? If you're here, can you raise your hand? Over here up front. Okay. We also have in the top 3 David Gustafsson. Is David here? Over there, David. And then we also have Mr. Celia and His Friend by Jae-Hang Lee. Is Jae-Hang here? Jae-Hang over there. Congratulations. So for the top 3, let's look a little bit at how they work on the inside. So we have Jae-Hang over there. We have Zhongxia and Brandon over here. And we have David over there. First we'll look at Mr. Celia and His Friend against QQ. What's under Mr. Celia and His Friend? 2 reflex agents with carefully designed evaluation functions. Defensive agent always chases nearest invading enemy and tries to escape if it gets scared. The offensive agent goes straight to the closest dot, eats a power pellet if possible. Once the offensive agent eats a single dot, it immediately returns home to collect the point. QQ, also known as Broken Bot. Offensive agent is a depth 2 minimax agent that prunes immediately on depth. Locations of nearest food pellets are cached to speed up computation. Evaluation function maximizes score, moves towards food, avoids dead ends when ghosts are nearby, and returns home if carrying lots of food. Defensive reflex agent with evaluation function that minimizes distance to the closest invader, minimizes distance to food that is closest to an invader, and avoids dying if opponents get a power pellet. All right. Try to think which way might play out better. We're about to watch a game between the 2 of them. So in red, we have Mr. Celia and His Friend. In blue, we have QQ. All right, let's see how this plays out. Broken Bot is taking the win here. This means we have in third place Mr. Silly and his friend. This is not how we determine the ranking. We play a lot of games, compute the ELO score based on that, but the games we're showing here is just one game that is showing third versus the team that either might be first or second, and third loses the game that we picked. All right, let's now look for first place. QQ, which we already talked about, versus Dino. Dino runs alpha, beta, minimax, only considering agents within 10 squares to expedite search. Iterative deepening to use as much of the allotted compute time as possible. Wait as it goes near the middle in passive mode. If an enemy attacks, go on the defensive and chase them. If a hole opens in their defense, take the opportunity to run after food pellet. Only attack when there is a guaranteed path to the food. All right, let's see how this plays out. QQ versus Dino. Here we are. Different maze. Let's see how this plays out. Broken Bot / QQ in red. Dino in blue. Whoa. QQ / Broken Bot is up by 7. Just too late to go make up for that. So QQ / Broken Bot wins by 7 in this game, and also in the overall ranking came out first. So let's project the full rankings here. We have our top 3 filled out. Congratulations to Jihang, David, Jongsha, and Brandon. We'll have more competitions coming up. There will be no contest related to Project 3. There will be no contest on Project 4, but then Project 5 will have a competition that will also be the final contest of the class competition. Okay, so look out for that. All right, back to working in our foundations of probability, getting ourselves ready for the next 5 or 6 lectures in this class. Probabilistic inference. Probabilistic inference is about running calculations with probability distributions that get us information that we want. The reason we have to run calculations is that typically the way you're able to specify a distribution in the most convenient way ends up specifying it in a way that you can't directly read out the answers to the queries you have. Your queries will be about something else, and now you'll have to do a calculation that transforms the specification of the distribution into an answer to the query that you're getting. For example, we might be interested in a conditional distribution. What's the probability of on time giving no reported accidents? But we start from a joint distribution. When we do this, if an agent does this, the result will call the belief of that agent. And so at any given time, our agents now will have beliefs of the world. They won't think the world is in this state or that state after a certain action. They'll say, after this action, or this measurement, I have this belief over what the world could be like. Probabilities can change. You can do a probability calculation conditioned on no reported accidents. Then in addition to that, you measure something else, namely that it's 5 a.m. right now. And then the distribution will change, and you now have a probability of 0.95 of being on time as opposed to 0.9 before. Okay? If you get even more evidence, now you also find out that it's raining, your probability might drop again because now it's less likely you'll be on time. And so it's interesting progression here where as you get new evidence, you'll update your distribution, and the probabilities could go up or down depending on the evidence that comes in and depending on how these measured variables interact with the unobserved variable. here's a standard inference procedure that will work no matter what joint distribution you're given. You can always run this inference procedure for every query that we might give you. There are three types of variables. When we're given a query, in this case the query would be, let's actually project the query. This is the query. We're interested in the distribution over Q given E1 equals small e1, E2 equals small e2, and so forth. So we're given measured values for the E variables, E1 through Ek. We're curious about the Q values. And there are also other variables, namely H1 through HR, that live in our table, but that do not appear in the query. Okay? This is the most generic thing you can have. Some variables are in the query in front of the conditioning bar, some behind, and then some don't appear at all. Accordingly, we call them evidence variables, query variables, and hidden variables. Step one, you start with your full joint distribution, and you select entries consistent with the evidence. Okay? So only retain what's consistent with your evidence. So you look, every row that has E1 through AK taking on the right values, you retain. Everything else you get rid of. This is a lot like what we've done in the conditioning exercise that we did before. Once you've done that, you sum out over the hidden variables. So what does that mean? You'll have a new table where your evidence variables will always take on the right values, but then your query variables and your hidden variables will still take on all possible values, but you don't care about what value your hidden variables take on, and so you need to somehow get rid of them. The way you get rid of them is by summing over the values they can take on. We'll see examples in a second. So mathematically what that means is once you do this step one, you end up with a table that corresponds to, so what you're trying to compute is this thing over here. You have a table that has these types of entries. To compute this type of entry, you need to sum over all values the hidden variables can take on. This is marginalization. We're marginalizing over the hidden variables, getting rid of them by summing entries. And then we have an unnormalized distribution, and we make it sum to 1. So let's step through this by going through some examples, but this is a generic procedure that will always be applicable. Okay? And ultimately you end up with your conditional distribution that you want. So let's do this. Here is a first one. Inference by enumeration for weather. So what was the first step? Step one was to retain all the entries in the table consistent with the evidence. There is no evidence, so everything is consistent, so we retain the entire table. Okay? Next step, we're going to now sum. So we're going to now sum over the hidden variables. Okay? So what are the hidden variables here? Hidden variables are season and temperature. So we're going to sum over those. So what does that mean? We're going to be interested in a table that only indexes over weather. So the table will look something like this. Weather can be sun or rain. There'll be a probability for that. For sun, we'll look at everywhere in this table where we have the consistent entry with sun. We'll sum these together. 0.15 plus 0.1 plus 0.1 plus 0.3, which gives us 0.65. And then we'll do the same thing for rain, or we know that it's the complement, we have 0.35. At this point, the last step is normalization. We have to sum these together. But because this is a marginal distribution, we actually already know it's going to sum to 1, and there's nothing to be done here. So this is an exception. Only when there's a conditioning in the end, do you actually really need the normalization step. Let's look at the next one. Probability for weather given winter. And once again, do this procedurally. So weather given winter. This is our evidence. Season equals winter. We get rid of everything else that's not consistent with that. So let's get rid of these. Left with this part of the table over here. That was step one. Step two is that we're going to now sum over the hidden variables. So which are the hidden variables. In this case, this here is our query variable. This here is our evidence variable, and this here is our only hidden variable in this case. So we're going to sum over that. So we're going to build a table that effectively corresponds to probability of weather, comma, winter. Only variable is our query variable, W, which could take on the value sun or rain. Oh, sun or rain. For sun, we'll look at the corresponding entries, sun and sun, 0.1 plus 0.15, so 0.25. For rain, we look at the corresponding entries, rain, rain. That also is 0.25. We now compute the normalization constant at step 3, z equals 0.25 plus 0.25, which is 0.5. And then to get the conditional, right here we have a joint. To make that into the conditional of weather given winter, we need to divide by z, which is 0.5. We end up with 0.5 and 0.5. So that's the full procedure for this query. All right, let's look at the last one. So last one, we're interested in winter, weather given winter and hot. So this case, our evidence variables are sitting here. So evidence is about the season and the temperature. So these are our evidence variables. This is our query variable. There are no hidden variables in this case. We need to pick the rows consistent with our evidence. It's actually only one, or in this case, two rows. Winter, comma, hot is happening here, and then it's also happening here. Everything else we get rid of. So we're left with this part of the table. Then we build up the distribution jointly for W, comma, winter and hot. And here is W can take on sun or rain. For sun, there's only one entry, 0.1. For rain, there's only one entry, 0.05. Now, to make this into a conditional distribution, we need to normalize. So we need to compute z, which is a normalization constant, which is 0.1 plus 0.05, which is 0.15. We divide by 0.15. And that makes it into the conditional distribution rather than the joint. So this is very mechanical. You can write a piece of code that does this for you. Somebody gives you a joint distribution. You can write a piece of code that, based on a query, goes to step 1, step 2, step 3, returns the conditional that was asked for in the query. Any questions about this? Yes?
Which part of this was the summing out of the hidden variables?
Okay, so that's a good question. So for this last query here, the summing out, there was nothing to be summed over. So it was a trivial step because there was no hidden variable in this query. For this one here, the summing out did happen because there was a hidden variable, namely the one that's not mentioned here, which is temperature. Are you asking about the second one?
Yeah, the second one, like what part of the calculation?
Okay, let's explicitly show the summing out in the second one here. So, second one, this is the query variable. This is the evidence variable. And this here is the hidden variable. Okay? So this has all three types of variables. Step 1 was only keep what's consistent with the evidence. Evidence says winter, so we get rid of everything up here. Now we're left with this table over here. Okay? This table represents the distribution for temperature and weather, comma, winter. Okay? We want to go from that to the distribution for just weather, actually, let me scoot it over a little bit. We want weather, comma, winter, and then later we'll normalize, okay? So to get weather, comma, winter, we need to get rid of this temperature variable here, okay? So weather could be sun or rain. For sun, we sum over all values the hidden variable can take on in this remainder table here. The hidden variable, when you're here is sun. Hidden variable could be hot or cold. And so we sum over these two entries. And so we have 0.1 plus 0.15. That's how we're summing over the hidden variable. Same thing happens for rain, which is living here and here. The hidden variable temperature varies. It could be hot or cold. We sum over the values that hidden variable can take on. And then in this case, we get 0.05 plus 0.20. So that's where the summing happened. Any other questions about this? All right, so now we can do inference on any joint distribution, and you can do it by hand, or you can write a piece of code to do it for you. Let's leave this. Okay. A couple of obvious problems that we're not going to address in this lecture, but we'll address in the next 5 lectures, is that the worst case time complexity and space complexity of this procedure is pretty bad. Because you're actually working with a table that has a size exponential in the number of variables. Okay? So keep that in mind. We're going to have to come up with a way to do this computationally more efficient than we've seen so far, and we'll see how to do that. But at least we know that procedurally, if we have enough compute time, we can answer any inference query at this point when given a joint distribution. It's a question, though, how do you get the joint distribution? Well, you can compose things. So, for example, if you look at the joint over x and y, you can actually write this as the marginal for y times the conditional for x given y. Why can you do that? Definition of conditional probability. Conditional probability for x given y is defined this way. You just move the y to the other side, you get this equation over here. And so what we see here is a way to attain a joint distribution by never needing to specify one. You can specify marginal over y, conditional for x given y, and then from that you can find the joint. So here's an example. Let's say we were able to specify a conditional for weather, a marginal for weather, a conditional for dry or wet. Given weather, we can build up the joint. How do we build up these entries? Well, wet and sun appears here, and sun is here. We multiply those together, and this will be equal to 0.1 times 0.8, which is 0.08. That's how we build up every one of those entries. Okay? We can expand this procedure. Rather than doing this just once with a marginal for one variable and then a conditional for another variable, you can repeat this. If you want to build up a joint distribution for 3 variables, you can write it as the marginal for variable 1 times the conditional for variable 2 given variable 1 times the conditional for variable 3 given variables 1 and 2. And so now we have a procedure to build up a joint distribution over 3 variables without ever having to explicitly specify it, but we can build it up from these 3 components. Okay? This notation here, what this means, it's a product. So if I say, for example, product over I from 1 through 5 of, let's say, I, that would be the same as 1 times 2 times 3 times 4 times 5. If I say product I equal 1 through 3 of xi, that would be equal to x1 times x2 times x3. What we see here, it's a product of conditional distributions. We ordered our variables x1 through xn, and then we say the joint among all those variables is the distribution for x1 times conditional for x2 given x1 times conditional for x3 given x1 and x2 times conditional for x4 given x1, x2, x3, and so forth. And any joint distribution can be written this way, where we don't have to specify the joint. We can just specify distributions for individual variables conditioned on some other variables, which is often a lot easier to do than specifying the full joint. Why is this always true? Like, Why can we always write things this way? Well, let's do this by example. Let's look at the very first one here, and you'll see the pattern. So what is going on here? We have px1 times x2 given x1, which we know is equal to x1 comma x2 divided by probability for x1. Then the last one is x1, x2, x3 divided by the probability for x1, x2. And we see that things kind of just cancel out. And it doesn't matter how many of these you have. It goes to x4, x5. You keep following that pattern, things will keep canceling out. And indeed, you always have the joint distribution as a product of these distributions over single variables conditioned on preceding variables. All right. So we now know from a joint distribution how to answer any probabilistic inference query. We know how to build joint distributions from conditional distributions that are certain types of conditional distribution that we can combine together with the product rule or the chain rule. Now let's take a look at what often the use cases of this, which is essentially Bayes' rule. So when you have two random variables, you can factor that distribution in two ways. You can say, I'm going to build a full joint this way applying the product rule, or I could swap the roles of x and y and build the joint distribution the other way around. For the chain rule, this would be, you can use any ordering of variables. It'll still be a valid chain rule, so you have many ways of building the joint distribution. They're the same joint distribution, so we have that these two are equal to each other. We can now divide both sides by py, and we get this expression over here. Just move this thing to the other side. That thing there, that's called Bayes' rule. Okay? If you had been working in AI, or maybe back in the days we did math and statistics, 200 years ago, you could have named the rule after something like this. If you look at it, all it is essentially just applying the product rule in two different ways and then dividing both sides by py. That's all there is to it, but because this thing is used so often, it has its own name, and it's actually useful to know this equation without having to always first go back to how you derive it. Okay? Why is this at all helpful? Why would we care about this? Well, often what we want to do is we want to go from one conditional. So if you look at what we have here, we have on the left side the result of our calculation, conditional for x given y. And we see that we can get this starting from the conditional for y given x. So if it's easier to build a conditional for y given x than it is to build a conditional for x given y, you can build your conditional for y given x and then use it to infer the conditional that you really care about, which is x given y. Often that will be the case. Often what you'll do, for example, in the case of the ghost that you're trying to find in this maze, you're trying to find the ghost. If you try to build a model for where is the ghost given my sensory reading, that's really hard to do, because that depends on how the ghost is behaving. Does the ghost prefer to be near the top, near the bottom? Does it move around? There's a lot of questions you have to answer to be able to answer the question, what's the distribution for where the ghost is given the sensory reading? The other way around is much simpler. If you say, given the ghost is a certain distance away, what is my sensory reading going to be? That is just you calibrating your sensor. You're just modeling your sensor, which you build, which you can calibrate, and then you can use that in calculations like these to infer where the ghost might be. This px here would be some information about the kind of ghost you're trying to find right now. Maybe this ghost likes to hang out in the bottom right corner. Well, that would be encoded in the prior information about the ghost, which you combine with your sensor measurement to get out a posterior over where the ghost might be. So let's look at some examples. So this will come back and back and back, and some people might even call it the most important equation in AI. So here's a typical use case. You want to infer what's the cause underlying some effect you're observing. You're able to build a sensor that when you know the cause, you know the distribution over effects, and then Bayes' rule helps you combine that with a prior over causes to get out the posterior for cause given effect. So this here is often called a prior and this here will be called your posterior. Okay, let's say you're worried whether somebody has meningitis, and the thing you get to observe is whether they have a stiff neck or not. The model you then would have is something like this. You would be given a prior distribution on average, how many people in the population have meningitis, or maybe on average, how many people who come to a doctor's office have meningitis. When people have meningitis, there are statistics on how often they have a stiff neck. When they don't have meningitis, there are statistics on how often they have a stiff neck. That's what you build up ahead of time. Now, if somebody comes in, you want to know whether they have meningitis or not, you apply Bayes' rule, which is this thing over here, fill in the numbers, and you come out with some, in this case, whatever this number is will tell you the probability that they have meningitis given what you measured. Some things to keep in mind. This is just a probability calculation. It could be that the number that comes out of here is tiny. But if there are really bad repercussions for not treating it when it's there, even if it's a small probability, you might want to still treat assuming it's there, or you might want to make extra measurements and so forth. So keep that in mind. Okay, to wrap up here, I'll leave this quiz for you. Let's look at the ghost maze again when we have our probabilistic inference in action. So same demo we did at the beginning, but now we see the distribution. Equally likely for the ghost to be anywhere. That's our prior. We have a sensory model. We measure. Bayes' rule is applied to compute the posterior, and the numbers here are showing you the distribution over where the ghost would be. This can guide you where you want to measure next. Maybe we measure over here. Again, we used Bayes' rule to incorporate the measurement, the likelihood of the measurement given where the ghost is, to get a posterior over where the ghost might be. We can go again. Not a good choice. We can go again. Not a good choice again. How about here? Oh, that's starting to look better. At this point, maybe we're willing to go for it. 0.99. Up to rounding, 1.0. Let's see what happens. And we got it. All right, that's it for today. Next time we'll look at Bayes nets.